Faerman talking about modeling the circumgalactic medium.
Thank you. Testing again. Yeah. Thank you. I want to thank the organizers for having me here and giving me the opportunity to share the work to share the work I've done on modeling the circumgalactic medium with you. And this is a project I've been working on with my PhD advisor, Amiel Sternberg, and Chris McKee. I'm now a postdoc at the Hebrew University working with Avishai's group. But this is a project I've been working on for a while. And I like to start with this very nice paper, a short letter from 1956, basically predicting the properties of circumgalactic gas, its existence. Back then, this was a theoretical construct. And I think it's really amazing that today we have a growing body of evidence, of observational evidence, for the existence of gas around galaxies. And what I plan to do in the next 15 minutes, if you are still not too hungry, you'll bear with me, I'll present some observational evidence from multi-phase gas around galaxies relatively briefly for this audience. And then I'll show some work I've done on constructing analytic models for this circumgalactic gas. This is not exactly this, but hopefully it works pretty well. And I'd like to start with the observations. As I said, the first line of evidence is X-ray observations in absorption in the Milky Way, detecting 07 and 08 absorption. These lines are also observed in emission on the sky. And this is gas at temperatures above 1 million Kelvin. There's, of course, also a very nice set of observations from the Coast Halo Survey, detecting both 06 in the few 100,000 Kelvin regime. This is 06 absorption around Z of 02 galaxies. And cooler gas at temperatures of maybe around 10,000 Kelvin, traced by a bunch of ions from magnesium-2, carbon-2, silicon-2, 3, 4, etc. And I should say that there is, of course, much more observations of gas around galaxies. Here and in our modeling, what I'd like to do in this first step is focus on Milky Way-like galaxies and combine these different data sets from the Milky Way and the low redshift universe. Now, if we start with the Milky Way, then the first challenge in these X-ray observations of the Milky Way is that since we're looking at an integrated column density along the line of sight on the sky, we don't know exactly where this gas resides. And the possible options are all the way from hot gas in the disk to megaparsec local group IGM scale. And of course, the length scale, other than the curiosity, other than trying to find out where this gas lies, is of course important for the total mass estimate in this component of our galaxy. And there are different works from a while ago suggesting that this is probably not local group IGM, but these two options are still viable for the Milky Way in principle. And here is where the Coast Halo's observations are very important, because if you look at the column density profile as a function of normalized impact parameter, this is 06 from the Coast Halo Survey, as I said. The different markers are the data points. The magenta larger markers are the bin data. And here you can see that inside the virial radius, there's a relatively flat column density profile, but then at this radius something happens, and here you have mostly upper limits, and this radius is roughly the virial radius of the galaxy. So motivated by these observations, we set out to construct our analytical model for the CGM, and the goal here was to combine the UV and the X-ray observations of both the Milky Way and other L-star Milky Way-like galaxies in relatively local universe or low redshift universe. Our basic assumptions in this model are that on large scales, the gas is in hydrostatic equilibrium. So here, this is the virial radius. The gas distribution is extended as suggested by the Coast Halo's observations. For this equation of hydrostatic equilibrium, the gravitational potential we adopt is the Milky Way mass distribution taken from the Klippen 2002 model. And we allow for support, for pressure support, not only by thermal pressure, but also for other components such as turbulence and cosmic rays and magnetic fields. In our first paper, in our first attempt at this modeling from 2017, we had a model that reproduced very nicely the 06, 07, 08 observations with kind of a two-phase corona, one reproducing the hot gas absorption signatures, and the second for the warm gas traced by the 06. Inside each phase was essentially isothermal, constant temperature, and constant metallicity. But what I'd really like to focus on in this talk is our new model. Here, instead of assuming an isothermal gas, we assume an adiabatic equation of state with a constant entropy. Again, we plug it into the hydrostatic equilibrium equation. And what we get is a natural variation in the gas temperature. Here's a function of radius. Here the temperature varies. So yeah, for the hydrostatic equilibrium, as I said, we allow different components for the pressure support: thermal, relativistic fluid modeled with a gamma of 4/3, and turbulent support. In this attempt, this is characterized by constant velocity dispersion as a function of radius. So here in this model, we get natural variation in temperature from a few hundred, 300,000 Kelvin, which is the real temperature of the Milky Way, and up to about 2 million Kelvin in the central region. For those of you who visited Israel or maybe even lived there, you should be familiar with these temperatures. These are the day and night temperatures in Israel in August. So if you're planning to visit and haven't yet, you should probably wait for a different month. In this model, we also have a metallicity gradient varying from solar metallicity in the inner part to about 0.3 outside, as suggested by enriched CGM and IGM observations. We also include photoionization by the UV background, and I can talk about that later, how it affects the different ions. So a few words on the physical properties of gas in this model. We get the density profile as a function of radius, and the slope here is about -1 with radius, so it's fairly flat. This profile is consistent with RAM pressure constraints from Milky Way dwarf satellites, and this constraint from Salem 2015 taken from the LMC, RAM pressure 3 PM, the LMC. The total gas mass in this model from this density profile is about 5 times 10 to the 10 solar masses, similar to the Milky Way disk mass. And we also show the pressure profiles, and the important result here, I think, is that there is a significant amount of non-thermal pressure that's required in order to reproduce the observations that I mentioned. So how does it work compared to the observations? We match the 07, 08 absorption columns observed in the Milky Way. In this plot, you can see that our black curve matches fairly well the Cos-Halo 06 column density profile. And we also match the dispersion measure to the LMC. Comparing our model to the X-ray emission observations, we're a bit low on those, which may be explained by the fact that this X-ray emission comes from the denser disk gas closer to the galaxy. If we want to try and produce some predictions for future observations or trying to suggest what to do next, one thing would be to try and search for extended CGM in the X-ray, again, addressing this question of where the X-ray absorbing gas resides. So we have predictions for the column density profiles of 07 and 08 for future telescopes such as Athena and Hubs. We can also try and test different models, such as this our new model versus the isothermal models, either ours or others, by different ions. I think Joe mentioned this yesterday, with neon 8, magnesium 10 at low redshift. And this can be done with LUVOIR in the future. And we also have predictions for the Y parameter and the electron density profiles and dispersion measures, as can be characterized using FRBs. So this is nice, but this is just for the warm hot gas. As I mentioned, the Cos-Halo's observations also show a component of cool gas So this is this picture showing the silicon-3 column density profile. And another challenge is that simulations and observations of galaxy clusters show that gas with low cooling to dynamical time ratio, maybe warm-hot gas with this low ratio, may be unstable and condense, forming a cool phase. So I want to combine these two challenges and take this to explain this. And here's how we'll do it. In our model, what I'm showing here is the dynamical time, which is basically the free fall time in the Milky Way halo, is the black curve. And the magenta curve is the cooling time in our CGM model. And you can see that at the virial radius, the ratio is fairly low at about 2. So definitely within this McCourt and Voigt et al. Regime of condensations. So we allow some fraction of the warm hot gas to cool and form the cool phase. The volume that has been evacuated by the condensations will be filled by the expanding warm hot gas, which then causes its cooling time to increase. Once the cool phase is formed, this is the full picture of our CGM. This is my take at a simulation. This is low resolution. I think it's not yet converged, but I'm going there. So these are cool clouds in this warm-hot ambient medium. The warm-hot gas is dominant by mass, and it's the temperature, as I mentioned, between a few 100,000 Kelvin to 2 million. The cool gas is in pressure equilibrium with the warm-hot phase, and its temperature is set by the UV background at about 10 to 20,000 Kelvin as a function of its density. What you can see here is, you've already seen this. This is the warm-hot gas density profile, and this is the local cool gas density profile, which is the inverse of the density things, of the temperature ratio. So now we can try to compare the properties of the cool gas in our model to the Cos-Halos observations. And I want to stress that in our model, the cool gas properties are not tuned to anything. They're basically set by the warm-hot gas properties and the UV background properties. So here you can see the H1 column density profile as a function of the impact parameter. Again, the markers are from Cos-Halos, specifically the Prochaska 2017 paper. And the solid line is our model. What I didn't mention, and I'll do this quickly, is that in our model, the cool gas forms at large radii initially, where this ratio of cooling to dynamical time is low, and then we allow it to migrate inwards. So these two lines are gas before migration in the dashed, and after migration, you can see that it can reproduce the large scatter seen in these cool gas observations. This is the plot of the ionization parameter. And one interesting thing is that in our model, the total cool gas mass is about 4 times 10 to the 9 solar masses. And this is consistent with Molly's paper from 2014, but it's significantly lower than the mass estimated in the paper that presented these observations. So I think there's something interesting there. However, we can also compare it to earlier Cos-Halos observations, specifically the low metal ions. So these are carbon-2, carbon-3, silicon-2, and silicon-3 from Jessica Work's papers. And you can see that here there is a much larger variation in the data itself. At a given radius, you can see both measurements and lower and upper limits. And I think our model does a fairly decent job at reproducing this, especially as I said that it wasn't tuned in any way to reproduce these, as opposed to the warm-hot phase. I'll stop here and summarize by saying that we constructed a phenomenological and analytic model for the multi-phase circumgalactic medium. It's a universal model combining observations of the Milky Way and other low redshift galaxies. It produces a fairly massive corona, but albeit with a low cool CGM mass. And we produce observations for future, we produce predictions for future UV and X-ray observations. That's one important thing. The other is it would be, for me at least, very interesting to extend this model to vary with halo mass, go to higher redshift, and link it to galaxy properties and different feedback physical prescriptions. Thank you, and I'll be glad to take.
Questions? Stacy K.
So you mentioned that the significant non-thermal pressure is required to actually explain the observations.
Yes.
Do you know what fraction of non-thermal pressure do you actually need, and is it consistent with any simulations like that? Actually, how do you compare the results to simulations?
I think so for the pressure compared it qualitatively, so let me start from the beginning. The amount of, the ratio of thermal to non-thermal pressure in this new model varies with radius. At the real radius where it's highest, it's about half and half. It's even closer to, it's dominated by the non-thermal pressure. Thermal pressure about 30–40% of the total. And this is basically required to reduce this flat 0.6 column density profile. That's the main thing. That's the main driver there. Our density profile, which also the fairly shallow slope is a result of that non-thermal pressure support, is consistent with some observations, with some simulations. I think, now I can't remember whether the slope in the Fielding et al. Simulations is lower or higher. Jonathan, do you remember what's the slope in Drummond simulations? Maybe? I think it's a bit flatter than most. But I think other simulations do see non-thermal support. Where it comes from, I think it's a different, interesting question.
Yeah, 50% sounds a little large at the very early radius. It might be possible that when you turn on the feedback, you can blow up the gas and you can lower the density that way as well without actually having to move significant.
Yeah, it has to be blown out all the way to the real radius. I don't know. It is important to say that at the real radius in our model, the division is roughly equivalent between turbulence, magnetic fields and cosmic rays, and thermal. So turbulence should be significant there too, right? So maybe we can discuss this later.
Okay, last question. Yeah.
So it varies between solar inside and 0.3 outside. We basically put it in by hand, both the profile and the values themselves. I would say that the metallicity values, the metallicity values themselves are not constrained, but I think what's really constrained by these 0.6 observations is the product of the density and metallicity. And I don't think you can vary these either way by a factor of more than 2. So, for example, I can increase the density by a factor of 2 and then lower the metallicity outside to 0.1, 0.15, but not much lower, I think.
Okay, thank you. So let's thank all of this morning's speakers again.